So for the t-test that we've talked about and the z-test, the critical value was on the sampling distribution in between the population and the observed samples. But things are a little bit different with an ANOVA. So what I want to do now is explain how the F distribution works. So the F distribution is kind of like the t distribution or the z distribution. It's the distribution we use for our critical value to decide whether or not we're going to reject the null hypothesis. So for the F distribution, we'll start with our observed sample distributions. We have 3 of these. These are all frequency distributions. And we'll say that this is intro exam scores, research design exam scores, and stance exam scores again. We'll keep the values the same as they were before. 100, standard deviation 10, sample size 33. The next step will be to calculate the variance of the population. So this is just like we did before. So this is the variance within. This is just like with the t-test. So we take the variance of group 1 plus the variance of group 2 plus the variance of group 3 and divide by, so we're taking the average of these, so we just divide by the number of groups. And remember, this is only, you can only do it with a simple formula if your sample sizes are all the same. So we have 10 squared 100 plus 10 squared 100 plus 10 squared 100 divided by the number of groups, 1, 2, 3. So our guess at the population distribution, if the null hypothesis is true, its variance is going to be 100, or its standard deviation would be 10. The next step to understanding how the F distribution works is to create a distribution of sample means. And recall again, this is all assuming at this point that the null hypothesis is true. If the null hypothesis is true, remember all of these 3 samples are from the same population with the same standard deviation. Our best guess is that standard deviation is 10. And now we want to figure out what the standard deviation is of this distribution. It's standard error. So that's going to be standard deviation here divided by the square root of the sample size. So it's 10 divided by the square root of 33. And 10 divided by the square root of 33 is 1.74. Notice that 1.74 was the same standard error estimate that we got when we did Tukey's post hoc test, the HSD test. And so it's really just the standard error that you expect in the sampling distribution with this population standard deviation. So I want to remind you that this is a population distribution of individual scores, because now we're going to create a different kind of distribution up at the population level. We're actually going to take the mean here, right? So this is, if the null hypothesis is true, what we expect the variance to be for our observed sample. So we're going to take this 1.74 and we're going to put that up here. But to get back up there, we want to go from a standard error, a standard deviation of this kind of distribution, to a variance of a population. So we've got to go back up. And again, like when we were calculating the ANOVA, we need to do the reverse process. So the standard error equals the standard deviation divided by the square root of n, and we want to have this squared, so we want this to be the variance because an F statistic is a ratio of two variances. So we need to turn this into a variance. So we're going to square that. We'll square this, and then we need to get the S squared by itself. So we have SE squared. If you square to n, you get n. So we'll multiply both sides by n, and that's going to equal the variance up here. So this formula will let us take the standard error and turn it back into a variance. So our sample size was 33 for each of these. And remember when we made this sampling distribution, our n was 33 for every sample that we got to create this distribution of sample means. So this n will be 33. Our standard error is 1.74, and we're going up, and then we're turning it into a variance. We need to square it. If you take 1.74 and you square it and multiply that by 33, you get 100, which is the same as what we had here, which isn't surprising because we actually did the same math to go from this 10 down to 1.74, and we're just reversing it to get back up here. So this 100 is the variance we expect if the null hypothesis is true. Remember, on our F statistic, our F ratio, it's the variance between divided by the variance within. So this bottom is that 100. And so if the null hypothesis is true, that's how much we expect our three means that's how much we expect for our three means for them to produce as an estimate of the population variance. So I want to point out that now that this 100 is a variance. It's not an individual score. It's a variance of a distribution. So these are variances. And they are variances at the population level. So this is going to be a distribution of population variances, assuming the null hypothesis is true. So this isn't really something that we've looked at in the past. The F ratio, the F statistic, is actually a ratio of those two kind of variances, but it didn't have a distribution. But our F distribution is going to be right up here. So these sampling distributions that we use for our inferential tests are our Z table, our Z distribution and Z table, our T distribution and T table. Those are designed to accommodate sampling error, right? And what we're trying to figure out is what's the probability of getting the observed sample or samples if the null hypothesis is true. And so what we need to be able to do is figure out, assuming random sampling from the population, how extreme do these means have to be to suggest that they aren't from this one population, right? So the null hypothesis in this case assumes that the variance estimate from these three sample means will come up to the population to be 100, but we know that there's some variation due to sampling, and so the F distribution handles that. And this is how you could think about what it's doing. What you could think of it as taking one sample mean from here for this group at random, and do that for two other sample means. So you take three sample means from this distribution. Right, you calculate their standard deviation, a standard error, and you put that up here. So sometimes you'll get three sample means whose standard error equals 1.74. Right? So that'd probably actually be the most common occurrence. And those would have to translate them from a standard error to a population variance, right? With 1.74 would be right at 100. So that's actually going to be the most common frequency of the variances that we would expect. Sometimes when you randomly sample these three samples from this distribution, you'll get a standard error that's smaller, right? And so you might end up with a variance estimate, say, of 50. The smallest possible value you can get, right? Since this is the square root of a squared value, the smallest possible value you could ever get is 0. You can't get a standard deviation below 0. Of course, you could get really extreme scores. You could end up getting 150. And really there's no limit, right? Remember, this is a distribution that has no end to it, which means that here there's actually no end to what you could get here. So let's say that we get a distribution, we'll say the distribution looks something like this. I'm not exactly sure what its shape would be, but the most common kind of standard error I'd expect would be the same as the actual distribution, but 1.74. And then it goes down to 0, that's the absolute bottom, but it goes on forever. Right, so these are the kinds of variation you'd expect due to random sampling from the sampling distribution going back up to the population variance estimate. Right, so what this is a distribution of S squared betweens that we would expect if the null hypothesis is true. Because remember, these are the kind, this is what we think of the populations like if the null hypothesis is true. This is what we think the sample means would look like if the null hypothesis is true. And if we take sample means from here, 3 at a time, which is what we need because that's how our study is set up, and then we see how those vary if the null hypothesis is true, this is the expected variation in the numerator of our F statistic. And this is all if the null hypothesis is true. And remember when we did the Z distribution and the T distribution, right? That's again the distribution if the null hypothesis is true, and we're hoping to find an observed sample that's so extreme there, so unlikely that we'll reject the null hypothesis and decide that population is not where our sample came from. All right, so now we have a distribution of expected variances between groups if the null hypothesis is true, and we already know what the denominator is of our F statistic formula. It's always going to be 100. So now what we can do is we can create, or we can calculate F ratios or F statistics expected if the null hypothesis is true. All right, so we'll have a column for the variances between, right, and these are if the null hypothesis is true, a column for the variances within, and then the F statistic or the F ratio that you get by dividing the variance between by the variance within. So for our variance between, it can go all the way down to 0. It can't be any lower. And we'll just plug in some values on here. These are just example values. 50, 100, and they'll give us a sense of what these F ratios look like. And then let's just put in a really big number like 1,000. The variance estimate from within is always going to be 100. Right, and then what we'll do is divide the between by the within. So 0 divided by 100 is 0. 50 divided by 100 is 0.5. 100 divided by 100 is 1. 1.5. And this would be 10. Right, and this could go on forever. So there's the F ratio will get bigger and bigger and bigger with no limit. Okay, so I've cleaned up the space a little bit just because I needed more room. And I've put new axes in here. And this distribution is going to be a distribution of expected F ratios. It's going to be F ratios here. So it's a frequency distribution of F statistics, or equivalently F ratios, right? So the bottom is going to be 0. We got 1.5, 1.5, 2. It'll go off, and remember, there's no limit at the end. And it can't go below 0, so it's going to be at the bottom here. 1 was going to be the most common. And then it'll go off forever in this direction. All right, and remember, and the reason you can think about it having a minimum of 0 is it's a ratio of two positive numbers. It's got to be positive because these are squared. And so you could never have a negative number. And because of that, what we've got here is basically a floor effect, or there's an absolute minimum, and so you end up with a positively skewed distribution. And so that means for an F distribution, the F critical values are always going to be on one side. They're always like a one-tail test. There's no way you could do an F test that's like a two-tail test versus a one-tail test. All of your alpha is going to be over on the one side in all cases. So if I drew it like this, the F critical looks like it's something like 2.5 would be the F critical for that particular case. And one last thing I want to point out about the F distribution, which is what this is here. This is the F distribution. Is an F distribution has a different shape depending on two things: the degrees of freedom between the number of groups, -1, and the degrees of freedom within. And so you could think about why it's the case, because this n equals 33, that relates to the degrees of freedom within, and the standard error of this distribution. And the degrees of freedom between, right, that's the number of group means, that's here. And that'll influence the variation when you're creating this distribution. So there's a different shaped F distribution for different combinations of degrees of freedom between and degrees of freedom within. And that's why when you look up an F critical value, you need to know both of these to actually get the F critical for the test that you're currently doing.